The human story has always been tied to the ground beneath our feet. For thousands of years, every tool, every structure, every invention was shaped by gravity's invisible hand. But imagine lifting that hand away. Imagine an environment where fragile materials don't collapse under their own weight, where liquids form perfect spheres instead of splashing apart, where crystals can grow without distortion. This isn't science fiction, it's the blueprint for the next great industrial revolution. Factories in orbit. And unlike the revolutions of the past, this one won't be confined to continents or oceans. It will unfold in the silent expanse above our planet, where human imagination meets the raw laws of physics in their purest form. Subscribe, like, and turn on notifications to stay ahead as we uncover how zero gravity could reshape the way we build, heal, and innovate. Right now, orbiting just a few hundred kilometers above us, NASA, Axiom Space, and private companies are running experiments that could flip manufacturing on its head. Take fiber optics, for example. On Earth, when molten silica cools, gravity pulls tiny imperfections into the strands. Those flaws scatter light, lowering efficiency. In microgravity, companies like Made in Space have shown that fibers can be drawn up to 10 times clearer than their Earth-made counterparts. That difference could mean data networks transmitting faster, farther, with less energy loss. The before and after is dramatic. A cable that normally loses signal over 100 kilometers could stretch thousands without repeaters, slashing infrastructure costs worldwide and transforming global communications. Think of undersea internet cables, only now crafted in orbit, reaching further, lasting longer, and reshaping the flow of information. But fiber optics are only the beginning. Think about pharmaceuticals. Proteins in your body fold into delicate three-dimensional shapes. When researchers try to crystallize these proteins on Earth, gravity causes them to clump or collapse. In orbit, however, crystals grow larger, more symmetrical, and easier to study. That precision could lead to new drugs for diseases like Alzheimer's, Parkinson's, or even stubborn cancers. Imagine the ripple effect. Clinical trials accelerated by years, cures emerging sooner, and once untreatable illnesses finally yielding to breakthrough therapies. This is not about astronauts tinkering in space labs with tweezers. The vision is automated. Robotic factories running 24/7, powered by the sun, producing goods too perfect or too delicate for Earth's environment. We aren't just sending rockets to explore space anymore. We're turning space itself into the factory floor. Imagine orbital assembly lines, each one packed with machines that never sleep, where production isn't limited by land, pollution, or infrastructure, but only by imagination and orbital capacity. NASA has been leading microgravity experiments since the space shuttle era, but it's private companies that are pushing commercialization. Axiom Space, for instance, is developing a commercial segment to attach to the International Space Station, with plans to eventually detach into a fully independent orbital factory hub. Think of it as a Lego block in space. Start small, then snap on more modules as demand grows. Sierra Space envisions inflatable habitats doubling as production facilities. Other startups are exploring orbital foundries for alloys, crystal growth platforms, and even tissue printing labs for organ development. This approach lowers risk, allows testing at smaller scales, and creates a pathway from science experiment to industrial output. Each modular unit could specialize, one for biomedical research, another for fiber optics, another for metallurgy, orbiting together as the world's first true industrial park in space. Each modular unit could specialize, one for biomedical research, another for fiber optics, another for metallurgy, orbiting together as the world's first true industrial park in space. Why go to all this trouble? Because gravity is a stubborn designer. On Earth, crystals grow crooked, metals settle unevenly, and biological tissues collapse before they can take shape. In orbit, all of those constraints disappear. Imagine semiconductor wafers without microscopic dislocations or medical implants engineered with flawless precision. It's like removing the distortion from a mirror. Suddenly, everything reflects the way it was meant to. The physics are elegant. Surface tension, diffusion, crystallization, and even combustion all behave differently without gravity tugging them down, opening pathways to products impossible on Earth. What seems exotic now could become the standard tomorrow, much like plastics or semiconductors once felt futuristic, but quickly became everyday necessities. And yet, there are challenges. Launch costs remain high, though reusable rockets from SpaceX and Relativity Space are cutting prices by an order of magnitude. Reliability is another hurdle. An orbital factory must withstand radiation, thermal swings, and the brutal reality that if something breaks, you can't just send a technician in overalls to fix it. Every system has to be designed for autonomy, redundancy, and fail-safe recovery. This is manufacturing at the edge of engineering. It requires AI-driven monitoring, self-repairing robotics, and an unprecedented level of precision in design. Some companies are even developing swarm robots, tiny machines that could collectively maintain and repair orbital factories, a futuristic twist on industrial maintenance. Every system has to be designed for autonomy, redundancy, and fail-safe recovery. This is manufacturing at the edge of engineering. It requires AI-driven monitoring, self-repairing robotics, and an unprecedented level of precision in design. Now picture this, it's 2035. You walk into a hospital, and the doctor prescribes a drug tailored for your condition. A drug whose protein structures were grown in orbit, far more effective than Earth-made alternatives. Or maybe you work in data infrastructure and your company just deployed cables spun in space, instantly boosting global bandwidth by 50% without laying new lines. In another industry, lightweight alloys forged in orbit enable aircraft that use 30% less fuel, shrinking costs for airlines and reducing carbon emissions. The impact filters down to everyday life: cheaper internet, faster cloud services, safer flights, better medical outcomes. This isn't a distant dream. It's a decade-long horizon. Imagine entire supply chains recalibrated around products born in zero gravity. Does a whole new industrial era in space sound exciting to you? Subscribe, like, and turn on notifications so you never miss the future unfolding in real time. Let's go even deeper. Microgravity also allows for the development of perfect spheres. On Earth, droplets flatten, but in orbit, they stay flawless. Why does that matter? Because perfectly round structures can be used in high-precision instruments like gyroscopes and optical sensors. The difference is like comparing a hand-drawn circle to one drawn with a compass. One works, the other works flawlessly. The applications range from GPS systems to telescopes that peer deeper into the cosmos. Astronomers dream of mirrors so precise they could capture faint light from Earth-like exoplanets, while defense engineers imagine navigation systems that remain accurate even without satellite signals. One small improvement in orbital precision could cascade into advances in defense, astronomy, and everyday consumer electronics. And then there's metallurgy. Alloys mix differently without gravity pulling denser elements downward. That means materials with more uniform structures, stronger bonds, and fewer weaknesses. Think of a skyscraper's steel beams. Today, they must be over-engineered to compensate for microscopic flaws. Tomorrow, space-forged alloys could mean lighter, stronger buildings, cars, and aircraft. The ripple effects cascade. More efficient engines, safer planes, even cheaper electric cars as stronger materials reduce weight. Additive manufacturing in orbit could extend this advantage further, creating composite parts directly in space that cannot be transported from Earth. Entire rocket engines could one day be printed in orbit, ready to power spacecraft outward. The economics are fascinating. Right now, it costs roughly $2,000 per kilogram to send something into orbit with SpaceX's Falcon 9. That's down from $20,000 just 2 decades ago. Starship aims to cut that by another factor of 10. If that happens, it becomes economically viable to launch raw materials, manufacture in orbit, and return only the finished high-value products. Fiber optics, crystals, pharmaceuticals, all small, high-margin goods with enormous value density. A single suitcase of orbital fiber could be worth tens of millions on the ground. The profit potential is staggering. Some analysts project orbital manufacturing as a $1 trillion market by 2040, rivaling the semiconductor industry. Imagine the first $1 trillion company born not in Silicon Valley, but in low Earth orbit. While we dream about futuristic products, there's already a factory in orbit today. The International Space Station has hosted Made in Space's 3D printer, which successfully printed tools and parts without resupply from Earth. That experiment proved the concept. If you can print in zero gravity, you can eventually manufacture anything. The ISS isn't just a science station anymore. It's a pilot plant for humanity's next economy. It has hosted over 3,000 experiments, many focused on material science, biology, and manufacturing, laying the foundation for a future where space stations serve as industrial parks, not just laboratories. Future private stations could take this even further, designed not for exploration but for production. But critics raise valid questions. Can these industries scale? Will we pollute orbit with debris as we industrialize it? What about safety when handling sensitive pharmaceuticals or advanced alloys? The answers are still unfolding. Engineers are designing orbital debris mitigation systems, while governments debate regulations for space-based intellectual property. Who owns a crystal grown in orbit? Who regulates the purity of a space-forged alloy? We are writing the rulebook in real time, with enormous stakes at play. Fail to regulate properly, an orbital industry could be throttled before it blooms. Regulate too harshly, and progress may slow to a crawl. A delicate balance must be struck, one that encourages innovation while safeguarding both orbital space and the Earth below. Consider the parallels. The first steam engines were clunky, inefficient, and expensive. Yet they unlocked the Industrial Revolution, transforming agriculture, textiles, and transportation. Space factories today are the clunky prototypes, costly, limited, experimental. But the curve is unmistakable. Each new test brings more efficiency. Each launch lowers costs. Each breakthrough inches us closer to a tipping point. Once reached, the curve will bend sharply upward, and the age of orbital industry will accelerate faster than most can imagine. History teaches us that revolutions look fragile at first, until they become unstoppable. Today's fragile experiments may be tomorrow's industrial backbone. What happens when we stop limiting ourselves to Earth orbit? Picture factories on the moon, where raw materials are mined and processed before being shipped into orbit. Imagine solar-powered assembly lines stretching across asteroid surfaces, harvesting metals and water ice at scales Earth could never support. Entire supply chains off-planet, feeding not just human industry, but future colonies. It sounds like science fiction, but so did reusable rockets 20 years ago. And yet, here we are. Could the next Fortune 500 be headquartered not in Silicon Valley but in lunar orbit? Could future billionaires build their wealth not in oil or software, but in asteroid metals? The questions spark imagination as much as they reveal possibilities. The future of space factories isn't just about better cables or cleaner crystals. It's about rewriting the relationship between humanity and gravity itself. For the first time in history, we can choose the environment in which we build. Earth is no longer the default factory floor. The cosmos is opening, and with it, possibilities we can barely begin to grasp. The real question is not whether we will build in orbit. It's how fast, and who will lead the charge. The nations and companies that take the first steps may not just shape markets, but shape civilization itself. So when you hear that NASA, Axiom, or a startup you've never heard of is testing a new material in orbit, don't shrug it off as another lab experiment. See it for what it truly is, the scaffolding of a new civilization. A civilization where we don't just live on Earth, we manufacture beyond it. The next leap in human progress may not come from a laboratory or a workshop, but from factories floating silently in the void. Subscribe, like, and turn on notifications to stay informed. This is Tech Mythos.